Hi everyone, this is Ruchi. I, along with Deepkala, will present the work we have done on classifying high volume DNS traffic and the solutions we implemented in Rust using, using some new methods and techniques. So, is Deepkala's slides visible?
Yes, they are visible.
Yes.
Okay.
We didn't actually come with code snippets per se. Actually, it's more like I want to talk about how we got Rust and how we faced some challenges in the project and how we used to use Rust to overcome those. So initially, when this idea was floated, we wanted to go with C++, but then as Karthik was pointing out in his previous talk, we in the earlier projects we had some trouble with the C++. Always it was about memory pointers, and so we wanted to try Rust. And at that time, Rust was a fast growing community. And once we started learning Rust, we all liked Rust and we decided to go with it, convince the client also to go with it. So the problem here was the client wanted to classify high volume DNS traffic, which was they wanted near real time processing, which came to around 15 million packets, DNS packets per second. To handle this, there were 4 phases in the project. One was data collection. Basically, your DNS traffic hits the client's DNS servers, that's DNS server. So here we collect the DNS packets and then they are forwarded to an enricher via this load balancer. There will be more than one server here, which will at peak time generate 15 million packets per second in whole. So this packets are then forwarded to the enricher, where we may perform some lookups, and each packet gives one enriched record. So per second, we are talking about 1 million to 15 million enriched records per second, which for analysis purpose, we then ingest into data warehouse like structure. So to implement some policies and other stuff, we had a policy server. That was other one. So data collection, data enrichment, policy applying stuff, and data ingestion, which will give us time to give us where we run some analytics and stuff for the client there. Out of this, the data collection part and the DNS server was run by an agent, which was fully written in Rust. So was the enricher. The enricher running this system to handle this type of traffic, we had to, it can be run on any type of orchestration platform, basically Kubernetes, which can handle, wherein because we are based on traffic, we needed to horizontally scale out basically. So it can run on Kubernetes, it can run on any container orchestration platform like Azure virtual machine scale set. So those are the things that we run. So the enricher also was written wholly using Rust. For testing purposes, we also had to come up with a simulator, which also which needed to generate around 15 million packets per second, which also we wrote using Rust. We found Rust very easy to match on. It was nice to work with. And Rust things which are usually difficult. We actually usually find pointers, and when we have a production system running this high volume traffic, it's very easy to have a memory leak, which will be really difficult to fix. So Rust we found very easy to code. But here we are going to talk about 2 main challenges that we faced when we had this project. One was though the classifying this DNS queries was of immense value to this client. When we wrote this code, we had 2 serious challenges. One of them was because we had to load balance and horizontally scale out based on traffic. The agent and the client here, we should go back here. The agent running on the server and the server agent running on this DNS server with this data collection part, and there is an enricher here which is written in Rust. Both of these are connected via a TCP connection. So when we had a load balancer, Azure load balancer here, which the connection goes via the load balancer. So technically the load balancer is supposed to distribute traffic based on the load here. It is supposed to the connection is supposed to go to different enricher instances at different point of time. But because it was a TCP connection, that was not possible because it was a persistent connection. The load balancer cannot break the connection, and thereby it was not possible to distribute the load. So to do that, we had to implement a multi-connection based solution in Rust, by which the connections were able to intelligently switch. This instead of one persistent connection, the agent will go up with one connection to. We went with dual connections. Basically, instead of one connection between the agent here and the enricher here through the one, we went with dual connections. Basically, one active connection and one passive connection. So whenever an agent wanted a connection to the enricher, it will request for a connection. So this is a normal TCP connection. We went for Tokyo runtime environment. So it will ask for a connection to the server. The server will give back two connections, one active, one passive. So the agent will start sending traffic using the active connection. After a specified time limit, the agent will shut down the active connection, switch to the passive connection. At the same time, the agent will again request for another connection, thereby refreshing the passive connection. That way, after a fixed minute, say 5 minutes once or 3 minutes once, that time limit was can be dynamically changed basically. So based on that time, every X minutes once, the agent will refresh the connection to the enricher. Thereby, this simple solution actually let us break the persistent connection, this is the TCP connection, thereby giving a chance to the load balancer there to distribute traffic. And this led us in future to when we ran this for 15 million packets on orchestration platforms, that is Kubernetes and VMSs. This was the main thing that allowed the load balancer to distribute traffic across all the enricher instances. This solution is a cloud native stateless solution. Like I mentioned here, it's a very scalable solution in Rust, which is still successfully running in our client environment, where it was successfully tested for a peak traffic of 15 million packets per second. It's handling 15 million packets per second. The test, like I said, was carried out using simulators. That is, we basically wrote DNS tab and a simulator on top of it. We basically used stream captured DNS packets, and then we ran that in a loop. So each we can run 50 simulators, 60 simulators. Thereby, we increased the load, tested this for 15 million packets per second before putting it in the production environment, and it's still successfully running. Okay, so this was one of the challenges we faced. The next part of it, my colleague Ruchi will take over. Thank you, guys. You have any questions? Something? Shall we go now or at the end?
So there are two questions in the chat. Is the DNS server internally hosted? And the second one is, what does an enricher do?
Okay, yes, the DNS server is internally hosted. It's part of the setup, yes. And the enricher, what the enricher does is it looks into the packet and see the client is one of our telecom companies, and they wanted analytics run on the DNS traffic which passes through their servers. So enricher base.
Yeah, just adding to what Nicola said, enricher, basically we have some data in a packet, and that data is taken and divided into, let's say, categories, or divided into some sections, and we are able to add some more information to it, perform some analysis on that data, and make it data which is more useful.
Basically, these enriched records are pushed into a data warehouse from which the client can pull out some reports which they can use basically. Over to you, Richi.
Okay. Yeah. Right. So, okay, coming to the second problem, we know that global variables in Rust are not as flexible as they are in other languages. So, global variables is something we used for this DNS enricher itself. So this challenge was that we want to update global variables in Rust, but we can't do them using our known approaches of using a mutex and giving this variable to each thread, or using a read write lock or a RefCell. So all of these either give us inadequate performance, or they did not give us good results. So we came up with a different solution, and I'll talk more about this problem and the approaches we tried initially before moving on to the actual solution. Next slide, please, Deepkala. Okay. Okay. So as you can see, the challenge was that we have just a second here. Yeah, so we have three hash maps, which are these global variables, and we want to do lookup from these hash maps into multiple threads simultaneously, and also update the map, this map which is the global variable, as and when required. So in order to access the same map in all the threads, we can either declare the hash map globally, or if we initialize the hash map in the main thread, then passing them to each thread requires cloning. Now the problem with cloning is that this cloning this whole map will slow down the process, and it will lead to a lot of data, lot of repetitive data in the memory. So then we come on to then we thought that okay, this is probably not a way to go forward. We'll come and declare the hash maps globally. So we know that in Rust we have a macro known as lazy static. So using the lazy static macro, we know that it's not the variable declared using lazy static is not mutable, and it can't be made mutable without using the RWLock or mutex. That too, the problem with RWLock and mutex is that it was slowing down our performance and not giving us the optimal results. So we thought that maybe using RefCell to make the variable mutable will work, but RefCell update doesn't work across multiple threads. Again, we could make the update, but across multiple threads, it was giving a problem. So the other way to go was using static mute. So as we know that static mute, these are the two keywords in Rust again. So the problem with static mute was that it needs a constant function, and constant function doesn't allow for tuple, for loop, etc. And what happened in our case was that we needed some way to populate this hash map. This, let's say we create a static mute hash map. We wanted some way to populate it using a text file. We have some data in a text file and we want to put it in a hash map. That is what our requirement was. So there was no way we could go ahead without using something like a for loop, or without iterating through that file. So again, this was a no go for us. Now, after trying all these methods, we implemented another solution with some basic logic. So, Deepkala, can you go to the next slide? Right. So, now we know, like I mentioned just now, that all the data coming into the hash map is coming from a text file. So, once we have what we did instead was there was the concept was that we would have this text file, the new text file coming in at a polling interval, let's say at 15 minutes, or let's say at 1 hour. So after every polling interval duration, we'll have a new file with us coming in from the policy server, and we would need to create a hash map. So what happens is, initially when we just start our program, we have a text file coming from the policy server and we create a hash map for each thread. Then at polling interval, we have let's say a text file too coming in from the policy server. We take a difference of these text files, let's say using a command line tool like diff. So using that, we can see what the differences are, and the additions, they can be added, whatever changes are there in this between the new and the old file. These changes can be made into a hash map that will be like a small, let's say a 5-6 entry hash map, and we will use a function called append in the hash map to add these new entries to the old hash map. So like it says, extend original hash map in a thread with the diff hash map. So this is how we thought that we can avoid the overhead of cloning of, let's say generating, let's say we have 60 threads, so generating 60 big hash maps every time at polling interval. That can be avoided just by taking a simple diff in the within the text file and making that diff come to the original hash map using the extend function in Rust. Yeah. That was the solution. So with some part of Rust, like the extend function in hash maps, as well as some basic logic of using difference of text files, we were able to get optimal performance, and we were able to get the data correctly into all the hash maps. And yeah, so we also debated a bit on the way on the let's say the hashing functions that we have. So we drew up a comparison between some pretty common hashing algorithms like XX hash, C hash. But even on checking the performance that way, we saw that there was a difference, but not much of a performance difference. This is what actually gave us a good performance. Like performance was going up with this approach. Yeah, so that's about it. Thank you so much. And yeah, we'll answer the questions. You can see some questions in the chat window. Okay, so somebody has asked, packets aren't encrypted. So, right, packets are encrypted, but we are not going into the detail of how they were decrypted and how we were able to get the data out of it. But yeah, packets are encrypted.
And yes, someone has asked about using ARC RWLock on a hash map. Using the locks under this one, see this client wanted this enrichment to happen in near real time, like I told you. Putting a lock, any type of lock, we tried ARC, mutex, RWLock. Putting a lock on any of these actually slowed down performance a great deal.
Right. And I can see Fennel has posted the link of our blog as well. Thank you so much for that. I was about to come to it. We have also written a blog about the same in our as part of our Wipro Tech blog series. So do check that out as well.
But all the mutes, like Abhijit is pointing out, yes, we don't need an ARC mutex or RW lock if we are ready to go with all the mutations taking place in one thread. But in this case, there was a main thread which actually was all the readers. The write happened on a asynchronous task which we were using out. So we needed to share between both this because it would involve multiple threads, that is write and read. We faced this problem, classic read-write issues. The lock was slowing down performance. Like we were saying, we initially tried, like Ruchi was saying, an arc mutex, read W lock. We went through a series of things, evaluated performance. Because the volume of huge volume of traffic we're handling was very huge, we were not able to go with any of those. That was significantly bringing down performance, and performance was major benchmark here.
Okay, so Aziz is asking how the
The
benchmarking is
benchmark,
done to test the performance. Deepala, would you
like
like to
I
explain that?
Yes, Ruchi. Like I said, see the what the client wanted was near real-time performance. The incoming packets coming in should be enriched, and they should be able to see it immediately, almost at zero time, which was what we were hoping for. Um, we used simulators to generate traffic, like I said, and then we were able to achieve near real-time performance. Initially, handling 15 million packets itself was a problem, because though we were talking about horizontal scaling, breaking persistent connections, that the load was huge, and we faced server crashes. So each and every thing had to be overcome. Once we were able to safely handle 15 million packets per second, we got near real-time performance. Yes. Enriched does not actually mean decrypt. Enriched in this case, see, but the DNS packets are not encrypted. We will be able to, the literature will be able to read those packets. That was not an issue. The issue was even for enrichment, like Ruchi is talking about, we were maintaining certain categories, and each category had its own hash map of data. And the hash map itself will have millions of entries. So we need to do lookups on these hash maps for each packet. We're talking about 15 million packets per second, 15 million packets per second, 15 million lookups. And we need them to be written into a file, ingested and available in near real time. So that was the performance benchmark that we were working on. And so we went through several cycles of coding, several discussions, and came up with a solution, which is now finally running successfully on the client system. So Fennel is asking if the locking was shifted to a file.
The locking was not shifted to a file actually.
There was no lock at the end. Like we said, the code actually did the diff of the changes. Whenever there's a change in the hash map, we got a diff of the changes and passed it along to this thread. The way the hash map changes were handled was this way. Ruchi, you want to go through this again? I think the Fennel is asking about this again.
Right. So, okay, I'll just explain the approach again. So, the RWLock is what we were using on the hash map variable inside the code. So, instead of doing that, as it was slowing down our performance, what we did instead was we created hash maps for each thread, but to maintain performance, what we did was create a hash map originally, create one hash map initially, and then after every polling interval, we will take the diff from the text file, between the two text files, and then add this diff back to the hash map. That is the approach we were taking. And in there, in that text file, there was no lock that was being implemented, so there was no OS level lock there, and that is why it didn't create any performance issues for us as well. Okay, what would happen when one thread was writing text file 2, but another thread was trying to read the diff file? Deepkala, would you like to take through that?
Yes. See, like we said, the main thread was where we were getting these hash maps, and these hash maps, the read was happening in several other threads which were running. It was a multi thread, like I said, it was we were running in a Tokyo runtime environment, and the server for each connection would spawn off an asynchronous task, and this hash map had to be shared with all these ones by the algorithm that we showed you, the diff creation and everything. We moved the that is the extending part, the diff ending part, everything into the main thread. Thereby, the shared the asynchronous tasks for sharing the hash map will all be read threads. They don't do any write. So the write was limited to the main thread. And when one thread was writing to it, that can be seen. As long as there is only one write and multiple reads, it will not matter. There's one change coming in, but the others will still be, other threads will still be able to read the file. Initially, we had more than one write. Only when you have a, like Ruchi was pointing out, only when we had a mutable hash map, which was shared among that, we needed to put a lock on it, because more than one thread will be trying to write to the same hash map. Once we brought it down to one write and multiple reads, the issue was resolved. And how does this affect disk IO performance? This technically was not affecting disk IO performance. When we put a arc mutex or a read write lock on each of the hash map, like I was saying, there were 15 million packets per second. There would be some filtering, but even considering that each of this asynchronous, each of this integer instances may be handling 1 million packets per second, not at peak time, we are looking at 1 million lookups. We had 4 hash maps, so 4 million lookups, and that was a lot. So when you add the overhead of arc mutex or a read write lock on top of it, it was affecting time. The time taken to process every packet and write it to the blob was it was making a huge difference. Like I said, the client was very particular upon performance. The system had to be stable. It had to handle 15 million packets per second, and we should get near real-time performance, wherein the data enriched records should get into the data warehouse and they should be able to see the analytics reports and stuff to be run on them. So it was affecting the performance that way, wherein the time taken to process, to enrich, and to ingest was getting higher and higher. Yes, we were not writing when we talk about in-memory cache and Redis. Yes, we had an in-memory cache. We are not writing each enriched record line by line. We had a number wherein we can say 1 million. We'll wait for the enriched instance will catch the enriched records. Say 1 million records. Once it hits 1 million records, it will write it into a file, which will then be ingested into the data warehouse. That was how it was going. Nirmal, yeah, I'm really not really sure about the hash map implementation in JVM. But yes, this n reads one write problem is a classic this problem which always happens. Yes, so there will be multiple implementations. Thank you. We did have an catch in the integer instance, which would so that we don't that way. That was another way by which we improved performance. The writing to the warehouse was not say we process one packet, enrich one process, and write one record. It was not that way. We used to that is a configurable limit, but say let's say we'll keep it at 1 million packets per second. So we catch 1 million enriched records, then write them all into a file, thereby ingesting it into the data warehouse that we used.
First of all, good attempt on subsistence programming problems.
Thank you.
Not necessarily easy to solve, even though conceptually they are. Why I mentioned that concurrent hash map is because what essentially they are doing, and I think someone has already mentioned it up there in the chat box, is that essentially you're not locking the entire map, you're locking a bucket, which is for the write, and rest of the n-1 buckets are open for reads, which is what I think finally you have arrived at. That's what I have understood from your presentation. Now my question is that you said we take the diff of a file. So let's say at a given point in time, the hash map has got 5 keys, which means 5 different file contents. Is that correct? Is the data structure like that?
Oh, sorry, what the flash map had?
At a given point in time, I take a snapshot of the map. So what does it contain? Let's say till then 5 files have been read from your policy server. So what is the structure of the map right now? I'm just taking a snapshot. I'm trying to understand.
So when we say the hash map has saved, see the hash maps, but basically data. We're talking about several categories of data.
Let me help you. My question was that I wanted to know what was the V in the KV of the map at a given point in time. You know the KV, the key and the value.
Yes.
Just trying to understand what the V is.
See, the value was a string, any string. See, this was all customer data, which we are using to enrich each of the packet that comes in. There were several categories that they had.
My question, you don't have to go into the details. I mean, I'm sure there are certain elements in this which you don't need to share. But my point is different. My point is that if a file comes at a time t, and if you want to find the difference, so where do you keep the previous n-1th version of the file? Because you need to remember, right? What was the previous version?
The n-1 version is in the main thread of the integer instance. The main thread of the integer instance already has that data. The integer instance running on any of this VMSS thing already has this copy of the data. What we wanted was a way to see this data will not change very often. We were expecting it to change maybe once every day, or at times not even that. But when the change happened, we wanted the change to be propagated through the hash maps and through the asynchronous tasks that were running. That is, if you remember, each of these tasks is spawned when we get a connection, when an agent requests the connection to this enricher instance. So that by they are for a particular specific amount of time, say 3 minutes or so. But these instances, these asynchronous tasks need to use this hash maps to perform this processing, to perform this enrichment. So in case the hash maps have to be updated at that point of time, the main thread will take a diff of the changes and pass along the changes. So we have a copy of the original entries already there. What we'll get is a diff along with that, by which the thread will extend the hash map.
Yeah, I understand what you're explaining, but honestly speaking, that's the part where I have questions about. But this may not be the session right now, because the point I'm trying to make to everyone here, and maybe there is a gap in my understanding, is that so your enricher are essentially dealing with two orthogonal inputs. One is coming from the DNS, other is coming from the policy server, and there is a temporal difference between these two, right? So keeping consistency is where I think some of your thoughts either have gone or should have gone. I'm just drawing up on my experience purpose, but thank you for clarification. That orthogonality of the inputs is very important when you deal with such situations.
Yes.
We say that look, okay, we'll poll, but poll is non-deterministic. You don't have a control of if at the penultimate second of the poll something has happened or not. You just don't know that. So yeah, I understand how you have dealt with it, but maybe there is a question. Maybe some other session. Perhaps I should go through the blog to understand it. Thank you.
Thank you.